Okay. Good morning.
Good morning.
ザビラさん、can you start?
Can you see my screen, Sensei?
Okay.
Okay, so I rerun the analysis for using directions.
Mm.
So the MY is 3,500 and the shear force is 2,009 Newton for 100%. And then we use
What is the size of
750 times 350.
okay, beam?
Yes, the beam.
Okay.
So we put the data here and then the C properties. And here is the properties of the metallic damper. And then here is the result for 100% to 20%. So every storage for L Central, less than 3. However, the Kobe, they have a little bit more than the limit 3.
So the result doesn't change so much.
Yes.
Could you go back
Yeah.
one again? Hmm. Okay.
And this is the accelerations.
How much ductility?
This
Okay. Okay. So ductility factor very different depending on the capacity of the damper. So 100%, which is 100%.
this one, beside the orange.
Okay, so if you reduce capacity of damper, ductility factor increase a lot. Okay.
Okay, and then this is viscoelastic. So we start from 100. So if 100%, the it will be 2,900 kilonewton, which is almost 3,000. And then this is the K and the C value. And for viscoelastic, we have to increase the damping factor
How did you decide omega? Yeah.
based on the open Stera 3D viscoelastic. So this is for viscoelastic. Based on the period of the building, 5.
0.5. Oh,
Yes. And then, so here the period is 0.5. And then we have K and C value. For this is for 100% is 10 layer.
Okay.
So this one.
Okay.
So, but for viscoelastic, we need to increase the damping and stiffness. So we try from 500 to 100. So it will be 50 layers to 10 layers. Okay, and then the result is this. So 100 is this here, 100%, and 500 light blue color here.
So in case of Kobe El Centro earthquake, the result different. But in case of Kobe,
Yeah,
a big difference.
100% is better than 500%. This is the other way around.
Okay.
Okay, and this is the accelerations.
Acceleration. So acceleration at the top floor from 800, more than 800 bar. Could you show me the acceleration of metallic damper?
Also almost 800.
800, okay.
And then this is the ductility or the viscoelastic.
Well, actually,
Mm.
there is no yield displacement, so
I see.
not to show that.
So ductility. Okay. And then I try to combine the damper. So if we combine here 500% from the 100% metallic damper, so this is the result. So the gray color is for Kobe, the orange color for El Centro, and the blue one is random.
Okay.
How about ductility sensing? Do we also have to show for the mixed damper or ductility?
Is this a ductility of metallic damper?
This is ductility for, it doesn't say it's metallic damper or not, just say from the moment open by 101. For example, this one. So so it just show like this. Last time we discussed there's the data beam is 0 because in here they only show for rebar, so it doesn't in here.
Sure. Okay, okay. Could you go back? So 100% metallic damper means,
Is 2,900 kilonewton.
so it is a capacity of steel beam.
Yes.
So ductility factor is more than 1 means steel beam may yielding.
The yielding at 40%, something. And the Kobe.
Go back to only viscoelastic damper, and you also showed ductility 11. Could you show me slide 11? So in all cases, ductility factor is more than 1. And in this case, this is the ductility factor of bending spring.
Bending spring.
Bending spring. So I want to know shear force of this case exceed capacity of steel beam.
Yes, sensei. 500 is time like we times 5.
Do you know how much of the member coupling beam?
From the steel beam?
Yeah, in this case, viscoelastic.
Viscoelastic damper.
And if you, for example, if you click max beam.
Max beam.
Is there shear force? No shear force.
It's only moment.
Maybe I should modify the program to get the but
we also can calculate manually from the moment and rotation.
So in this case, you assume bending spring is elastic.
Viscoelastic here. Yes.
Yeah.
Let me open this.
Yeah, so this is elastic, right?
Yes.
And this is viscoelastic.
Yeah.
So so I want to know, in this case, steel beam may start yielding.
Okay.
So I want to check force of the steel beam. One moment of the steel. Okay. Could you show me, it's the first slide, there is a capacity of moment.
Yeah, this one.
Yeah. 3,500.
Yeah.
Right?
Yes, sensei.
Could you show me?
Next beam.
No, in the text file. No.
In this one.
Yeah. So, which one is very large? Element number.
Power of 6.
For
Yeah,
example,
this
number
one.
3. Yeah.
Number 3.
Is this how much?
This is 1,400, around 1,400 sensei.
Is it larger than steel beam?
Steel beam is small,
500.
3,500.
Yeah. キロニュートンミーター。
Yes.
だから、センティメーターだと、500. Okay. Could you go back to?
This one.
Yeah.
It's the same. So 1,043 kilonewton meter.
Still less than 3,500.
Yes.
Okay. Not yielding. Okay,
This is
fine.
for random phase 500 viscoelastic.
But 500 is viscoelastic.
Yes, yes.
Okay.
And then after that, I try to combine the
Yeah.
damper.
Yeah.
So this what happened is 500 and the lowest metallic damper.
Yeah.
And then I also try 100% for viscoelastic and look for metallic damper. And the story drift a bit large. And then I also try 100% viscoelastic with 100% metallic. For 500 mm wall thickness, I think the building cannot resist for Kobe. So I try to increase the wall thick 100. And the story, I took 500 and 100 metallic damper, viscoelastic and metallic damper. And Kobe story drift is almost touching the limit drift.
You change the size of the wall.
Only thickness, yes. Because 500, we cannot. If you see 500 and 100, the Kobe is more than the limit drift. Yes.
How about the case of only metallic damper?
Only metallic damper is all Kobe sensei. It's more than limit drift.
How about the viscoelastic damper?
Viscoelastic is here. Also,
But almost
okay. Yes.
So if you adapt viscoelastic, you can success to. But in case of El Centro, it is that.
Yes, 400% viscoelastic.
400%. 400%. So this one looks okay. So this is 500. And this is also 500.
No, this is 100. Say 100.
100.
Yes.
So 100 is El Centro is the largest. And
Yes.
is the lowest.
Yeah, the other way around. It's like
Opposite. Okay. And if you combine both plastic and metallic, you cannot solve the problem.
yes. So this is when I combine 500 visco 100% metallic.
Metallic.
So the other way, the only way that I
Yes,
can.
yes. Out and Kobe. Recent and Kobe. And Kobe is larger.
Yes.
Mhm.
Little bit. And then I try to increase the thickness.
But if you increase the thickness, of course, it will be better. But
yes, yes, yes.
なんていうのかな。It's not our objective.
Yes.
Our
How about if already wall we stick to 700 something. So
But if you adapt 700, maybe brake is okay, viscoelastic okay. No need to combine.
combination.
No need to combine.
Here if we combine
Mm.
like 600 also, like slightly.
Well, this is very small. So,
Small, okay.
okay. If 500, not so big.
Okay. So so we can find the 40% metallic, the middle at fifth story, the temple start to you. So I think we can use 540% for metallic temple.
Is there, okay. Let's see acceleration.
Acceleration for this one.
In all cases, I mean, I'm curious about the top story. Always it is more than 800.
Okay.
Even you combine.
This is I combine. This is, I think it's slightly improved for the acceleration when we increase the wall thickness.
No, don't change the
Okay.
story change.
Okay.
I don't want to change the story.
I
So, okay, now let's try to your idea. I mean, putting it in middle story, and the top and the bottom is metallic damper. Is this your idea?
Side by side. No.
So,
In middle, left and right. Not top and bottom.
Could you try to reduce top story acceleration?
Oh, you mean the optimum position?
Yeah.
Yes. Top and bottom is metallic, and the middle is viscoelastic.
And
combine.
To control acceleration.
So the acceleration can reduce.
Really?
Let me open. Yeah. So this one, we just put viscoelastic, the hybrid damper in the middle, other is still beam. Yeah. This is for 600, 200 beam, and this is for 700.
But let's see. How can I see this graph?
Which one? Okay, so this one is 100% our temple locations. So if you can see case one here, case one.
What do you mean 100%? What do you mean?
Metallic temper is equal to the capacity of the steel beam.
Okay. How can I see, for example, what is the difference between this? acceleration.
Case 4 is there's no damper, there's no beam in the building, only couple shear wall. The yellow color.
No damper.
Yes, no damper, no beam, only wall.
Mhm.
Green color is where we put the only viscoelastic and metallic damper at the middle. And the top story and bottom story is the
But the acceleration is not improved, even larger.
yes. Right? Let me check. I think I did some. This one. Yes. Yeah, I think we have problem, but we are good with the story tree.
Mm. 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 About the viscoelastic damper,
Mhm.
you assume from 500.
Yes, 500. 500 to
I'm talking
1.
about not this one.
Mhm.
I mean,
But the other one.
yeah. 500 is maximum,
Maximum.
but you can increase more.
Yes, yes. If I increase more, I can increase more. So I increase by the size, the area, because I limit to 550 because 5 times is for the viscoelastic, and we also have to add the 5 mm of steel plate. So it's mm. So 10 mm times 50 is already 500 mm thickness only for the viscoelastic plate.
Oh, okay. But
I can
500
increase.
is a 50 centimeter width.
I
350
Yeah, 350.
width. Why it's the same width?
Why?
If it's a layer, maybe with you, why same width for different layer number?
Because we only control by the layers, you see. So every steel beam we can have same area for the viscoelastic. If we want to increase the capacity, we just can increase the layers.
Sorry, I don't understand.
If we area, so the shear area also increase and the K and C also increase. But I want to make the design I just control by viscoelastic layer the number of this.
Why? The capacity of viscoelastic depending on the depth.
The depth?
If you increase layer in the same width, the depth is getting smaller. So capacity of viscoelastic is depending on the depth of each layer. I think the depth is a constant.
What? You mean this one?
Yeah, viscoelastic.
I understand. You mean that I can just control the size, make it constant, and you want me to change the area based on the capacity. Actually, it can.
Viscoelastic, for example, there's a plate layer.
Yes.
And between there is a viscoelastic material.
Yes.
Right? And its deformation is this angle, gamma. And there was in each layer, is, well, if it's linear, shear modulus multiply gamma. Okay? So if you have 1, 2, 3 layer, I must write down thickness. だから、G じゃないの。gamma. So, yeah, multiply thickness. So this is a deformation of one layer. And maybe, こうやって、ちょっと、one moment. ですね。Okay, suppose, ですね。This is 350. Suppose this is one layer, and the deformation is delta, and angle is here. And even if you divide two layers, same 350, well, capacity, is the capacity different if you divide layer or three layer in same thickness, 350? I think the capacity doesn't change.
Okay. I think maybe I explain. I draw something. Okay, so we have, this is the viscoelastic, and here the weight is 350, and the height is 330, and this is the one area of viscoelastic.
Okay.
So this area also known as shear area will also influence capacity. So this is the formula. So we have K and C, G times the shear area divided by the thickness of the each layer. So the thickness we fix as 5 mm because fabrication is usually 5 mm, 10 mm, and 15. So we just fix as 5 mm thickness. And the area here, so this is the viscoelastic. And then we layer by, so this is the steel plate, and each layer and by layer. So one viscoelastic and metallic is equal to 10 mm. So if you want to increase the we either can change this one or the layers. So in this case, choose just to control the layer, viscoelastic layer. So the capacity also increase. The other way around, if you want to constant the viscoelastic layer, we can change the area of the viscoelastic. So if we want to increase more than
So each layer is 5 millimeter
thickness.
thickness.
Yes.
ちょっと待ってね。
And for example, this one have 50 layers. So 5 mm of viscoelastic plus 5 mm of steel plate and 10 mm. 10 mm times 50 layers, so 500 mm.
Oh, okay. So height, width, and thickness is
Yes.
another dimension.
Yes, this is thickness and this is the area of the viscoelastic
Oh,
only.
okay, okay.
Yeah.
Okay. So it means 250 millimeter in total thickness.
Only for viscoelastic. But if we add a steel plate, 500 mm thickness.
How much depth of the steel plate?
Depth of steel plate.
I mean, between layers.
It should be a little bit bigger than the viscoelastic.
No. If I look at the section of this, there are many layers,
Yes.
right?
Yeah,
And
it would be like
this is steel plate, and this
So,
is viscoelastic.
yes, it would be like this. And then there's another viscoelastic. And then this another steel plate.
So how much each plate?
Each plate thickness is a 5 mm. So this one 5 mm, 5 mm, 5 mm.
Okay, so if you multiply twice, it
Yes.
will be total
Yes.
almost. Okay, could you go back to the Excel file?
Yeah.
So in case of 50, 250 for viscoelastic, including steel, it will be 50 centimeter. 50 centimeter. Okay. Okay.
And then increase the capacity, we can change here. For example, I increase the thickness, so 400. So the capacity also increase. So it's also possible to acquire.
Okay.
So do you want me if I increase the capacity?
I don't know. What I want to change is top story acceleration more than 800. And even you change the capacity of damper, you cannot decrease.
Yes.
Yeah, this point.
Yes.
Or doesn't change much. You can control story drift,
Yes.
but acceleration at the top. Maybe is it difficult?
Most of the results here, for example, this is 900 copy. This is even larger, almost 1,000. And here, 1,000.
Yeah, but the 800 is always.
Yes. Yeah, if we use 500 viscoelastic, the acceleration will be at 800. But if we use 10% elastic, can like reach 800 to 1,000. So I think if we use bigger viscoelastic, maybe we can reduce the acceleration.
How about concentrating damper only top floor?
Top floor.
I mean around here. No damper
No damper.
in the lower part.
Only steel beam.
Maybe.
Okay.
I believe building will behave like a second mode, and the top story will be smaller. You can do it now?
I think I tried last time. And I tried a few cases, but I have to find where still. Let me check. Maybe someone can present first so I can find the Excel file and then show
Okay.
you later.
Yeah.
Thank you, Sensei.
Oh, Ataya-san, can you report?
Yes, Sensei. May I share this screen? Sensei, thank you for your comments about this figure. So I will correct this comments. According to here, Sensei, the definition of TMD change for each method. In this book, Sensei, the mass is divided the mass of TMD over the modal mass of the structure. For example, this is the second mode. So this is the mass ratio is 1%. So 10 multiplied to the modal mass is the mass of TMD. So it means that the mass ratio is mass of TMD over modal mass in both cases.
Yeah. But in your paper,
Yes, Sensei. This is
how do you define mass ratio?
mass ratio is overall totally is 3%, Sensei, for all cases.
You said the all cases 3%. The definition is
Sensei,
different
3%.
depending on the method, right?
Yes, Sensei. It is when it is equal, based on this paper, Sensei, each TMD has equal mass. M1 is equal. So it means total mass of TMD divided by the number of TMD. So MI, which is M1, M2, M. So mass ratio, if each TMD is equal to the total mass ratio divided to the number of TMD. As I did here in the equal mass, Sensei. Total mass of TMD is divided to the number of TMD, which is the mass TMD for calculation. But the total mass ratio, which is 3%, remained unchanged, Sensei.
So, for example, you as a total 3% of total mass.
Yes, Sensei.
Multiply total mass of the building.
Yes, Sensei.
Total mass of the building. So it will be TMD, right?
Total TMD mass,
total
yes, Sensei.
TMD. Yeah.
Yes, Sensei.
In case of method A.
Yes, Sensei. And divided to 3 TMD become 1%.
I know.
Yes, Sensei.
The mass ratio is calculated as 3%.
Yes, Sensei. In paper, they did it like this.
The number of increments. Total increments. So in this case, the mass ratio will be 3% divided by number of
TMD. It means 1%, Sensei, for each TMD.
Okay. And in case of method B,
it is divided to the mass ratio of, it means mass of each TMD divided to the modal mass of that mode. So mass ratio of each TMD is equal to the total mass ratio, since 3%.
But this is the same as total TMD mass, no?
It is total TMD, yes, since actually the mass ratio became the same as overall mass ratio, 3%. As I in the book, sensei.
Okay.
In method 1, because we have not any characteristics to discuss, so we have to divide the TMD mass to the number of TMD, because talking about something. But in here we are talking about modal mass. It means that each TMD is responsible to control that amount of mass in that corresponding mode shape.
Okay.
So we have this. Method C, we have two of them, participation factor and also effective mass ratio. So we have to calculate the mass ratio based on those two characteristics.
Okay. I understand now. Okay. Yeah, okay. Okay, fine. Yeah.
And I will correct all of them, sensei. And here, sensei, did you use equation 14 to calculate the period? Maybe you mean equation 15, sensei. Equation.
Maybe. Yeah.
Equation 15 is based on the Japan.
Yeah.
So although I didn't calculate for 7 story, sensei, but if I calculate based on that equation, it becomes 0.42. It is almost the same. If I round this number, it becomes 0.42. So I didn't calculate based on that equation, but if I calculate based on that equation, again, it's almost the same, sensei.
So how did you calculate this one?
I just assumed, sensei, for there are papers about how to assume the first fundamental period of a building. So I thought that for this amount is okay.
But to be consistent, it should be same method, right? So maybe you should mention equation 15 here. And also, it will be 0.42?
Yes, sensei.
So almost same. So you can just correct.
Yes, if I round it, it is 0.42.
Yeah. So there is not change so much. So
no, sensei.
You can use same figure, and you can mention equation 15 here.
Okay, sensei.
I noticed you made a mistake of spelling here. 7, you story, right?
Yes, sorry.
Yeah.
Yes, thank you, sensei. Yes.
No. Okay.
I will correct it.
Yeah.
And here, sensei, is this about table 1? Is this this is the complement of sentences, sensei? There I said that we have two models. One model with single TMD and one model with multiple TMD. But there I said that the model equipped with multiple TMD featuring 3 distinct mass distributors, which is A, B, and C.
Yeah.
So here I said that to ensure consistency, all models maintain the same mass ratio of 3%. If we sum these three values is equal to 21.
No,
there's
yeah,
three.
but why?
Yes.
but
So it,
You must mention this before. I mean, table one. So, where's the explanation about table one?
it is not exactly about table sensei.
But the table one is
But it is related to table one sensei. Related. They are related together.
could you show me explanation of table one? How did you mention?
Here, sensei, I said here, sensei, the mass values of TM based on the aforementioned methods of mass distribution in section in these two sections. So
Okay.
this is one,
No.
and here table one offer information regarding the specific mass values assigned to each TMD and different methods of mass distribution.
But you didn't mention how to decide this.
I mentioned previously, since this on base three methods. The table is calculated based on this. They said that
You didn't mention anything about 3%.
in here, sensei, so it is a overall methodology, but
I know about table one. Table one, the value in table one had it to be 3%, right?
yes, since all of the 3%.
But you didn't mention here.
So
People don't know why you 7 or 21.
mentioned somewhere in before that in here. You are right, Sensei. I didn't mention. So I have to mention before the table, maybe in here, Sensei.
No.
Okay, Sensei. Thank you.
Okay, but your paper is almost finished. So please send me again after you finalize.
Yes, Sensei, of course.
Okay.
Yes.
Good.
And there is no other comments.
Yeah.
I will correct all of them, Sensei, based on your comments, and I will send it again.
And how do you submit this paper?
Still, they didn't open the venue for the submitting in the website provided upload link. So
Really?
yes, because they will open it from 1st August and it will be available to 22nd of August, I think.
Okay. You must wait. Okay.
So and since they mentioned papers together with a cover sheet should be submitted in electronic format. So they didn't put any sample of cover sheet, so I don't know what they mean.
Well, there's a Japanese version of the format, and in this Japanese version, they didn't mention anything about cover sheet. I don't know why they put in English guideline only. So maybe not necessary.
Although I failed to ask, but they didn't respond about this.
Okay.
Yet. So this was my question, Sensei. And there was another thing, the ordinary page is starting from the second page. What they mean for...
I also don't know, so you can ignore.
Sensei. So I will be waiting for their response if they responded through email about this cover sheet, and I will share with you, Sensei, about.
Okay, good.
Yes, and that's all. Thank you.
Okay. Sarah-san, do you have anything you can show me?
Yes, I have. See this slide?
Yeah.
Oh, okay. First, I built an structure with no beam model in Stereo 3D, and next, 600 and 200, and steel beam 750 and 350 models in 3D Stereo 3D. And next, from this, I choose the steel 750 and 350. So I metallic damper 100 and the viscoelastic 100 model in Stereo 3D. So artificial whip from this storage drift. It's the better one is the metallic 100 and the steel beam 750 and 350 millimeter. And under the central web, metallic 100 and this 750 is a better one. So I choose the steel beam 750 and 350. Under copy earthquake, it is not good. Steel beam 750, but metallic 100 is good. For about metallic this is of metallic damper 100% to 20%, and the share capacity is 2,300. And this is wall thickness. This is metallic storage strip of thickness 500 millimeter. Under ear central wave, all of the but under copy is just only metallic 100 is a good. And the earthquake. And so it's called like for about risk 100 to 20%. This is a properties, and this properties is 500 to 100%. So we need to increase this. So we design to the one 500%. And this is viscoelastic storage drift and of wall thickness 500 millimeter, and under air central web this is all not good without viscoelastic 500 millimeter, and under the copy wave
wall thickness 500 millimeter is not good. All versions. So we decided to increase wall thickness to improve storage. So wall thickness is 6 millimeter. If wall thickness is 600 millimeter, under the air, just only viscoelastic the 100 is not good. But under the copy web, under the copy, 100 and the metallic 100, just only metallic 100 is good. So also I decided to increase the wall thickness to the 700 millimeter, and there is a under the air central wave. This is still viscoelastic 100% is not good, but under copy viscoelastic 100 and elastic 500 is not good. Metallic is okay. And next step is combinations of metallic and the viscoelastic damper. That's it.
Okay. So your work is very close to Zakura-san's work.
Yes.
Yeah. So please talk with Zakura-san. And we must make some story to make a paper. And okay. Okay. Thank you, Sarah-san. So shall we move to Zakura-san again? Zakura-san,
Okay.
do you get any new result? Oh, okay. So you put viscoelastic on the top stories. Your voice is off. I cannot hear. Your mic is off.
No?
Okay, okay.
Okay.
I can hear.
So this one, the first try to put metallic damper at the bottom and viscoelastic plus metallic at the top. So this is the result. I think the duration doesn't improve. And here, the other way around, if I put metallic on the top and the bottom, and at the top acceleration also doesn't change.
Okay.
And now, because we know that the wall without the beam have good accelerations, and here I try to put the damper at the bottom, with the beam on the top, and the acceleration also doesn't change here.
So maybe it's not to control the acceleration.
Accelerations.
Okay. Let's make the story simple. First, have a coupling beam with metallic damper only, and you have a story distribution.
Yes.
Right? And you can obtain same result by capacity spectrometry or displacement-based design. And the second part is coupling with viscoelastic material only.
Yes.
but we didn't discuss yet how to obtain this by capacity spectral method.
Okay.
So this is very important.
はい。
And we must follow the procedure.
うん。
Naki-san made a paper about how to obtain equivalent damping for the element with damper. This velocity dependent damper. だから、have you tried?
Yes, yes. So we tried last time based on the K and C of the first one we tried based on the first. The first one is based on energy,
Mhm.
and then the second one based on the moment rotations of the beam is the beam element in the stereo 3D. So, yeah, in the paper we have, this is the formula for the viscoelastic.
Yeah,
So
yeah.
energy and the
Yeah.
damping.
Yeah.
Mm.
So yes. This is a formula. So we can apply formula.
Mm.
エナジー、So first you do some over the
Yes.
coupling wall without beam.
Yes.
And you get the performance point.
Mhm.
And
And then we get the 1/250, the drift ratio. And then we put inside the Stera 3D. And then we can get the pushover for the 1/250. First
yeah.
Mm.
And also you can calculate omega.
Mhm.
I forgot.
That is 0.5. So the omega is 12.4.
And how do you get T?
Based on the first mode of Stera 3D.
First mode of stereo 3D.
But this also depends on the model itself, if we have damper or not. If it's only couple wall, I think, let me open here. So, for example, only have the omega for no beam damper. So this. So this one, the omega is, the T is 0.62.
But it's a linear. But if you push up to 250, I mean, actually, omega is this slope.
I see.
So if you adapt elastic, it's very high, but so it's getting a bit crack,
Mhm.
maybe to the wall.
Okay.
Maybe the omega,
It's
actually this
less.
omega square
Okay.
is a little bit less.
Okay.
But I must refresh my memory. Could you, okay, first you get the result by time history analysis.
Yes.
For metallic damper only, and the viscoelastic damper only,
Mhm.
and you get the same result. This is time
Mhm.
history analysis,
Mhm.
and another one is the displacement-based design.
Yes.
Displacement design, and to compare each other.
Yes.
So this is one objective of your research.
Mm.
And another one is you combine metallic damper plus viscoelastic damper. So we must think about how to obtain this result by, displacement-based design. So in this case, you must combine equivalent damping by metallic damper,
Yes.
equivalent damping by viscoelastic damper,
Yes.
and we propose to square root.
Mhm.
So I want to know if it works or not.
Okay. Okay.
And if you success to make a comparison,
Mm.
yeah, it will write one paper.
Okay, Sensei.
Yeah.
Understand.
Hmm.
I have one question, Sensei.
Yeah.
Do we start from steel damper metallic viscoelastic, or we start with couple shear wall with no beam, no damper?
Oh, maybe. I think so.
Start no damper, no
Mm.
beam. Okay.
Hmm. Hmm. It's also we must discuss.
Okay.
Or just the steel beam, not damper. I don't know which one is good. Well, anyway, メタリックダンプ。No. Yeah, let's discuss how to do.
Fine.
You
Okay.
can try, maybe.
Try to make story first. Okay, Sensei.
But
Thank you. Mhm. Yes, Sensei.
time is getting limited.
Don't worry.
Also, you must start writing.
I start the introduction, but I haven't finished everything. It's okay. I can do it.
Okay, maybe we can do it face to face. How about let's
How about Monday, Sensei?
Monday は、10のプラスで、真ん中プラス。I have time maybe only evening, 5 o'clock.
Okay.
Okay? 5
Okay,
o'clock.
Sensei.
Yeah. So please come to my room. Yeah. Okay. Anybody has anything to discuss today?
Since
Yeah.
about the frame model with the small stiffness and linear.
Yeah. Sorry, I check. I don't know. Same problem happens in case of Sawaya-san.
I don't know, maybe.
Taraya-san,
Yes, Sensei. In my case, I did not this problem, but I don't know. Maybe I have also not checked it with so less stiffness also, like the stiffness. And also in my case, the main structural time period was also very high. So maybe there are some numerical issues, but I am also not sure why this problem is occurring.
Do you change the time step to be small enough? Well, last time I told you.
Yes.
Right?
Yes, since I did it, so in case of without TMD and with TMD that is tuned to natural, both frame model and lamp mass has almost the same, and it is acceptable because there is something.
Yeah. When you change natural period of the TMD.
Yes, Sensei.
And also
yes.
you divide the time step very small, right?
Yes, Sensei.
Okay. Anyway, I don't have time.
Okay, Sensei.
Later. Yeah. And yeah, maybe after you come back from internship.
Okay. During this time, because I wanted to work at night about you.
Yeah.
If you had time during these 2 months, I will appreciate it because I want to use time at night.
Yeah. Okay. Okay. So shall we discuss next meeting? Maybe after I come back from Turkey. August, I'm how to say, I must go to Turkey, and after that I must go to Taiwan. But the 14 or actually I'm free. 14
Okay,
I'm free.
we can do 14, Sensei.
14 it's okay. So 10 o'clock 14 Monday.
Yes, Sensei.
Ataya-san, when you will go to internship?
I will go next Monday, 31st of July. Sensei.
Yeah, so you cannot join, right?
But because they have a summer break from 11 to 18 maybe, so in this meeting I can join. I don't know if I have something to present, but maybe in 14 I can join, Sensei.
Okay. So if you can join, please.
Yes, Sensei.
I'm also curious what you will do in the company.
Okay, thank you, Sensei. I will join.
Okay. Discuss today. Okay. So see you. Bye bye.
Thank you, Sensei.